What if you could know with absolute certainty whether any computer program you run would ever freeze or crash? It sounds like a programmer's ultimate dream, right? But as it turns out, that dream runs headfirst into one of the most famous and fundamental paradoxes in all of computer science, the halting problem. So let's just dive right in. I want you to imagine a single piece of software, a kind of master program, that could look at any other program, your web browser, a super complex AI, your favorite video game, and tell you with 100% accuracy if it's going to run to completion or get stuck in an infinite loop. Could a perfect bug checker like that even exist? I mean, a tool like that, it would completely change software development. It would be the holy grail, right? No more crashes, no more programs hanging forever. But to really get why this dream is impossible, we have to first understand the problem itself. Now, some programs are super easy to figure out. You look at a program that just prints "Hello World," and yeah, of course it's going to stop. Then you see a program that's literally told to loop forever. Well, no big surprise, it's going to loop forever. For these simple cases, we can see the outcome. But the question is, can we do it for every possible case? And this brings us to the formal definition. The halting problem isn't about figuring out one specific program. It's about the challenge of creating a single, universal program that could solve this puzzle for any program and any input you could possibly throw at it. So let's play a little thought experiment. Let's pretend this dream tool actually exists. We'll give it a name. Let's call it halts. You can feed the source code of any program into halts, and it spits out a simple, perfect answer. Yep, it halts. Or, nope, it loops forever. And for this to work, we have to assume this program is perfect. It is always right. No exceptions. Okay, so we've got our magical, all-knowing halts program. Now, let's get a little mischievous. We're going to use it to build something devious, a new program designed specifically to be a logical trap. And we'll call this one paradox. The logic here is simple, but it's incredibly sneaky. First, paradox takes a program's source code as its input. Then, inside, it runs our perfect halts tool to predict what that program will do. But, and this is the entire trick, paradox is hard-coded to do the exact opposite of whatever halts predicts. Let that sink in for a second. If halts looks at an input program and says, oh, that one's going to stop, paradox immediately throws itself into an infinite loop just to prove it wrong. And if halts says that program will loop forever, paradox immediately stops and exits. It is a professional contrarian by its very design. And now, for the main event. We've built our perfect logical trap, and it's time to spring it. This is the exact moment where the whole idea of a perfect bug checker completely falls apart. Here it is, the killer question. What happens if we take the source code for the paradox program itself and feed it back into paradox as its own input? We are literally asking paradox to analyze itself using the halts tool that's built right inside of it. And this creates an absolute, inescapable paradox. Let's walk through it. If the halts program inside predicts that paradox will halt, well, paradox is designed to do the opposite, so it has to loop forever. So the prediction was wrong. Okay, what if halts predicts paradox will loop forever? Well, then paradox is designed to halt immediately. The prediction is wrong again. Either way, halts makes a prediction that forces its own prediction to be false. It's a perfect contradiction. And there it is. That inescapable contradiction proves that our very first assumption, that a perfect program like halts could even exist, had to be false. It is logically impossible. A universal bug checker can't be built. The halting problem is, and always will be, unsolvable. Now, this isn't just some clever little thought experiment. This paradox is actually the core of a deep and profound mathematical proof, one that was formalized by one of the greatest minds of the 20th century. And that mind, of course, was Alan Turing. His mentor, M.H.A. Newman, once said that Turing's genius was in answering the question, what is a mechanical process? With the simple, brilliant answer, something that can be done by a machine. This idea was the key to defining what computation even means. You have to appreciate the time frame here. Way back in 1936, long before you could just go out and buy a computer, Turing proved the halting problem was unsolvable. He didn't use Python or Java. He used an abstract, purely theoretical model of a computer that he invented just for this purpose. He called it the Turing machine, and it's just beautifully simple. All it is an infinitely long tape, think of it like memory, a little head that can read, write, and move along that tape, and a basic set of rules telling the head what to do. That's it. It's the most fundamental computer you could ever imagine. But here's the incredible leap. Despite its simplicity, a Turing machine can simulate any computer algorithm that any computer in the world could ever run. So by proving the halting problem is unsolvable for his simple machine, Turing proved it's undecidable for every computer, past, present, and even any we might build in the future. So, okay, it's a really clever thought experiment, a foundational proof in computer science, but why does this actually matter today? Well, as it turns out, the implications are absolutely enormous. You see, this whole question didn't just come out of nowhere. It started back in 1928, when the great mathematician David Hilbert asked if all of mathematics could be decidable. Basically, could a machine solve any math problem? Then, in 1936, both Turing and another brilliant logician, Alonzo, independently proved the answer was a resounding no. The specific name, halting problem, came a bit later, but the groundwork was already there. And the ripple effect of this proof is just massive. For starters, it shows there are hard, provable limits to what we can ever know through computation. It's the very foundation of a field called computability theory, the study of what's possible and impossible for computers. It's also deeply connected to Gödel's famous incompleteness theorems in math. In short, it tells us that no matter how powerful our computers get, there will always be certain problems that a super algorithm simply can't solve. Ultimately, the halting problem is so much more than just a clever puzzle. It's a fundamental landmark in science, defining the very edge of what is computationally possible. And it leaves us with this really profound question to chew on. If computation has these built-in fundamental limits, what other unsolvable problems might be out there waiting just beyond the reach of our machines?